Hello and welcome to the second lecture of the CE468. Today I'm going to be talking about an introduction to the set theory, and then I'm going to be presenting a very interesting concept that is the regular expressions, and then we're going to see finite state automata and how the finite state automata can map one-to-one to the regular expression and vice versa. And then we're going to distinguish between the finite state automata as deterministic and non-deterministic, and we'll see how to convert a non-deterministic finite state automata into a deterministic one. So what is a set? A set is a collection of objects. So a set is nothing but a group of elements that share something in common, and they are put together in a group we call a set. The set doesn't have an order, and the elements in the set cannot be repeated. Anything can be actually represented as sets as long as discrete. Something like, the movies that certain actor has acted in, or the set of smartphones that were produced by certain company. Anything that has the discrete value, discrete nature, can actually be represented as a set. As you can see here, the set is denoted like this. Many of our sets are actually infinite, something like the set of integer values, or the set of values between two numbers that are float, real points. This is also infinite. So representing an infinite set is a little bit problematic because you can't really state all the elements that belong to this set. And that's why we use something what we call a set builder. And the set builder is nothing but a form of discrete mathematics that describes the set. So instead of mentioning all the elements that belong to this set, you can actually describe the set in discrete mathematics. And this way, you cover the whole spectrum that is being covered by this set. What is the universal set? A universal set is a set that contains all the possible elements in certain domain. So as an example, if we're talking about the universal set of the English alphabet, the universal set of the English alphabet starts with A all the way to Z. So you're not going to find a single letter in the English language that does not belong to this universal set. So that's the definition of the universal set. Now, assume that S is 1, 2, 3, and this is a set. In order to get all the subsets of S, you would say the very first subset of S is what we call the empty set. And the empty set is denoted as phi, and this is a set that has no elements. And then 1 is a set, 2 is a set, 3 is a set, 1, 2 is a set, 2, 3 is a set, 1, 3 is a set, and 1, 2, 3 is also a subset of the set. So for any set The set is a subset of itself. It's worth noting here that there's a huge difference between an empty set and a set of zero, because a set of zero is a set that contains element zero, but the empty set is a set that contains no elements whatsoever. So now, if we talk about the intersection of sets, it's as simple as this. It's every element that belongs to both sets. So if you want to get A intersect B, you would say all the elements that belong to A and belongs to B in the same time. So if you want to write it as a set builder, you would say it's an X, any element, X, such that X belongs to A and X belongs to B. Now, the concept of mutual exclusion is that when you get the intersection between two sets, you would find that this is kind of intersection is an empty set. So in other words, there is no common elements between the two sets. The union of the sets, if we want to write it as builder, in the same sense, it would be X such that X belongs to A or X belongs to B. And or here is a very important operator that will guarantee that the element is being repeated only once in the set. The complement of the set. What is the complement of the set? The complement of the set is another set that contains all the elements that do not belong to this set. So where would you get these elements from that do not belong to the set? Basically from the universal set. So if, as an example of this, if you say the the set of English letters and the set of vowels. So the set of vowels has few letters and the set of the English letters is the universal set. So if you get the complement of the set of vowels, that will be all the letters that are not vowels, which belong to the universal set of the English letters, but do not belong to the set of vowels. The cardinality is a very important concept, and we call it the magnitude as well. And the cardinality is the number of elements that belong to certain set. So if you look at this set A on the screen, 2, 4, 6, 8, 10, that would be 5 elements. So the cardinality of A is 5. Why? Because it actually contains 5 elements. So the cardinality is the number of elements that belong to certain set. Now, the concept of languages. What is a language? The language is nothing but a set of strings. A set of strings. Any language is nothing but a set of strings. The language doesn't have to be spoken and it doesn't have to be written. In fact, any system, especially discrete systems, that have rules that dictate how this system works, then this system has a language. So if you look here in the screen, the washing machine, It does have a language, rules that dictate how you can deal with this machine, and a sequence of operations, and an expected outcome. It does have a language. The vending machine, the traffic lights, the roundabout has a language because there are rules that dictate how the car will merge into the roundabout. The ATM, the lock, the light switch, even a soccer game has its own rules and it has its own language. So the language, just like any language, is defined by first the alphabet. So in order to say I do have a language, then first you have to come up with the alphabet. And then when you get the alphabet, you're going to build the strings that belong to this language using this alphabet. The alphabet is a set that contains all the symbols that build the strings that belong to this language. Just like how we say the English alphabet, any English word, it's composed and built out of this English alphabet. The alphabet takes the symbol sigma. So if you see sigma, this means a language. So now what is a string? A string is a finite sequence of the alphabet symbols. So for a string to belong to a certain language, it has to be composed of the letters that belong to the alphabet of this language. Very special type of strings, we call it the empty string. And the empty string is a string with a length of 0, and we denote it as lambda. The empty string belongs to actually any language. So the empty string is part of any language, unless the description of the language states that it cannot have a string with a length of 0. So now that we know what a language is, let's now define what a regular language is. A regular language is a language that is built with the main 3 operation sets that would be the union, the concatenation, and what we call a clean closure. Union, concatenation, and clean closure. The union we know. The concatenation of 2 sets is basically the cross product of all the elements that belong to the first set with all the elements that belong to the second set. So it's actually, if you have 2 sets, one set is A, B, and the second set is 1, 2, then the concatenation of this one, it was going to be A1, A2, B1, B2. So this example shows you how you would get the intersection, how you would get the union, and how you could get the concatenation. So now what is the clean star or the clean closure? It's called clean star, clean closure. The clean star is nothing but the set is being concatenated with itself 1 or more times. So instead of concatenating 2 different sets, you're going to have the set concatenated with itself 1 or more times. That's the clean closure or clean star. So, what is a regular expression? You can see the regular expression as a string generator. It's actually a mechanism to describe all the strings that belong to certain language. So it's a string generator that generates all the strings that belong to this language. It's worth saying that a single language can be described by multiple regular expressions. But in the end of the day, those multiple regular expressions are equivalent in giving the result of the strings that belong to this language. So the regular expression is nothing but a sequence of description of how the string that's going to be generated is going to look like, as you will see in the lecture. So if you have a language like this of a switch, as we have agreed before, anything that can be dictated by a discrete event has its own language. And in fact, something like the switch that you see here on the screen, it does have its own language. The alphabet of the switch is on and off. And the grammar, because the language, just like how it has an alphabet, it has a grammar that dictates how you can build the strings of this language. So the grammar of this system would be, if you are on, you can only go off, and if you're off, you can only go on. And so the regular expression would look something like this: on, off, or off, on. And of course, you can repeat this many times, so you can add the star for this expression, as you will see in the notes and the lecture. So a few examples for the languages. If you want to say strings that can start with either 0 or 1, and the zeros can exist anywhere in the string, so can the 1. So it's going to be 0 or 1 star. What is the star? It's the loop. It's the repetition of the expression. A language of 0 and 1 that cannot be empty. Cannot be empty, then you have to concatenate the 0 or 1 with another 0 or 1. Why? Because the star means 0 or 1 or more times. So if the star repeats 0 times, this means that the output of the repetition is an empty string. And since the language cannot be empty, the string cannot be empty, then you have to concatenate it with 0 or 1, as you will see in the lecture. And so on and so forth. That's how we describe languages in the form of regular expressions. Now, let's talk about graph theory a little bit. We all know what graphs are by now. They're nothing but nodes that are being connected with what we call edges. And the graphs can be directed graphs or indirect graphs. The directed graphs are graphs that have arcs with directions from one node to another. And the indirect graph are those kind of graphs that the arc do not have any direction. The finite state automata is a directed graph, so the arcs have directions. And the arcs describe the flow of tokens inside the finite state automata. If we go here, This is a finite state automata with few states, Q node, Q1, Q2, Q3, Q4, and you have transitions among those kind of states. So you have the transition from Q node to Q1, from Q1 to Q2, from Q2 to Q3, and from Q3 to Q4. As you can see, the start state is being pointed by a pointer, and the accept state is being drawn as double circle. For any finite state automata, you can have a single start state, but multiple acceptance states. The transitions are being dictated by the alphabet. So you cannot have a transition with a token that does not belong to the alphabet of the language the finite state automata is representing. So as you can see in this example, your alphabet is A, B, C. If you look at the transitions, there are either A or B or C. You can't have a transition D. Why? Because D doesn't belong to the alphabet of this language. But the opposite is true. So you can have symbols in the alphabet that do not show in the finite state automata. Why? Because the finite state automata could be representing a subset of the strings that belong to this language. It doesn't have to represent all the strings that can be generated by this language. What you can see here is what we call the state transition table. And the state transition table is nothing but an incident matrix that tells you the topology of the finite state automata. And it actually gives you a little bit more than just the topology, because it also tells you when you get certain input, where will you move from which state to which state. So the way we write the state transition table is the rows are the states and the columns are the alphabet that build this language. And then you say, when I'm at state 0 and I get an A, I'll go to state 1 as seen here in the example. But when I'm in state 0 and I get a B, I'll go nowhere, and that's why it's a phi. And when I'm state 0 and I get a C, I'll go nowhere, and that's why it's also a phi. You can have an enhanced design for this one. And instead of going to phi, if the only token that is expected when you are in Q node is A, then when you get B or C, you should be going to a reject state. When the string finally lands in an acceptance state, we say that this string has been recognized by the finite state automata. So this finite state automata that you see actually recognizes a single string, that is A, B, C, A. So if you get a string A, B, C, A, the string is being accepted and you land in your single acceptance states in this particular case, which is Q4. So let's see what happens here. Here is the string A, B, C, A that is being input to the machine. Now, when you get the A, you consult the table, and the table tells you, you are in state 0, and you got an A, you should be in state 1. And then, when you move to state 1, which is Q1, you get the other input, which is B. So you consult again the table and you say, okay, now I'm in state 1 and I got a B. Where shall I be? State 2. Here it is. And then you get another input that is C when you are at state 2. So you consult the table and it tells you that when you're in 2 and you get the C, you go to state 3. And then you get an input A, and when you get the A, you consult the table, and the table tells you because you're in state 3 and you got the A, you should be in state 4. It's worth noting here that this design allows that as soon as the string is being accepted, it can accept any other sequence that follows. In most of the cases, that's not the case. I mean, you should actually distinguish whether the string ends at the A or it has continuity. But because this machine is very basic and it doesn't recognize such thing, you would find that IS3, the last one, is also being recognized by this machine, because as soon as you land in an acceptance state, you never leave. Also, here for the IS2, if you get a C, you're going nowhere, so you remain where you are. Now this one, you will get the A, you get acceptance. Now even with the C that follows, you're gonna remain in your acceptance state. So the regular language is a language that is being recognized by a finite state automata. So for a regular language, you can build a finite state automata, you can build a regular expression. And as you will see in lecture, the finite state automata and the regular expression can be converted from one to the other. So if you have a finite state automata, you can get the regular expression. And if you have the regular expression, you can definitely get the finite state automata. Now, what is the difference between deterministic finite state automata and non-deterministic finite state automata? The answer is very clear. If you have certain state, and this state gets a few outputs out of it, if for every token that is being fed to the net, the machine, you know exactly where will you be landing, then this is deterministic. But if for a single input you might be in different places, then now we have a problem. Why? Because the machine is non-deterministic. And it's worth saying here that you're not going to be existing in two states at the same time. This is not the case. In fact, you don't know whether you belong to this state or that state. And that's exactly why it's called non-deterministic. Here are some examples of the finite state automata, and you can try to get here the regular expression. So for the first one here, every loop is a star. Every loop is a star. So try to figure out here from here how you can get the regular expression out of this one. The second one that you see, please ignore Q3. Why? And it was intentionally put here. If you look at Q3 here, Q3 tells you that if you land in Q3, you never leave. And Q3 itself is not an acceptance state. Then what is it? What is Q3? Q3 here is a rejection state. A rejection state. So the regular expression cannot model a rejection state. The regular expression only models the acceptance state. So if you try to model this using the regular expression, your expression is going to be huge for nothing. Basically, because you don't need to model the rejection state in the regular expression. So when you try to model this, you're going to model the Q node, the Q1, and Q2, and forget about the Q3 because Q3 is a rejection state. So please do not take it into consideration. Here are more examples of finite state automata that you need to think of and see how you can get the regular expression out of them. Here are more. Now, if you have a finite state automata that is non-deterministic, how will you get the deterministic one? Basically, by rebuilding the table. You're going to rebuild the table. So, when you're in a certain state and you get an input that will make you land in more than one state, you're going to create this new state that has more than one state. So, if you're in Q node and if you get an A, you can land in either 1 or 2, then you're going to create a state that is called 1, 2. And this state represents the case 1 or 2 in one state. And then when you're in 1 or 2 and then you get certain input, you're going to go to all the possibilities that if you were in 1, you would go to, and if you were in 2, you would also go to. And this is how you actually convert from a non-deterministic finite state automata to deterministic finite state automata. This algorithm has an output, and the output of this one is a deterministic finite state automata. So you will not find the case of having the non-determinism. You will end up having a graph that the transitions from any state is unique. So you would have a state like Q node, and the Q node has an output of A to state 1, but A will not exist for any other state, and so on and so forth. So you are actually achieving the uniqueness of the transition by changing the non-deterministic finite state automata to the deterministic one. Thank you very much for listening, and I'll see you next video.